we already have one expression for plane wave in section 5.2. In this session, I'm going to do some geometric construction for the wave so that you could refresh your memory and also look into the physical meaning of the expression. So suppose you have a k vector in space, and this k is quite important because you know now this k is perpendicular to the wavefront of the wave, and so it tells you the propagation direction of the wavefront, and the unit vector of this k is denoted by an. And given this k in space, in, for example, the XYZ coordinate system, then you can measure the angle of k with respect to the x-axis, y-axis, and z-axis. And if you project this k onto these three axes, then you can calculate the kx, ky, kz. So if you do so, you can express your k as k cosine alpha along x direction, k cosine beta along y direction, and k cosine gamma along z direction. And alpha, beta, gamma are the angles between k and x-axis, y-axis, and z-axis, respectively. So if you know the angles, then it will be quite easy for you to write down this k vector. So those angles are quite important, especially the cosine values of those angles are quite important. And there's a name associated with this cosine alpha, cosine beta, cosine gamma, and we call this the direction cosines. So now you have this direction cosines. Let's look into some parameters associated with it. So again, there's a k vector in space, and there's a plane wave propagating along this k direction. And you can see the figure here with the black and white parts to tell you the wavefront of the wave. And the period of this pattern give you the wavelength along k direction. And again, k is equal to omega square root of mu epsilon, equal to 2 pi over wavelength. And if you set a constant phase in the plane wave solution, then you can deduce this phase velocity of this wavefront propagating along k direction. And in the last session, we also deduced this constraint on k, x and ky and kz. On the last page, we also define kx, ky, kz based on direction cosines. So if you just put this the kx, ky, kz into this constraint, you come up with the constraint on these three angles. It tells you that if you choose two angles in space, then the third angle is already fixed. So alpha, beta, gamma are not totally independent. And you need to follow this rule to set the angles for your plane wave. And now let's try to decompose this k and look into the propagation of this wave along different directions. Well, to simplify it, I put the drawing on a two-dimensional space and just set gamma equal to 90 degrees. So this means that the angle of this k with the z-axis, which is going into the ball, or in fact, it's going out from this ball, is the 90 degree. So cosine 90 degree give you 0. So you know you only deal with the k along x direction and y direction only. So kx, if you project this k onto x-axis, then you have k cosine alpha. And you can look into the phase velocity of this wave along this x direction. Well, previously we always focus on the phase velocity along the wavefront direction, along the direction perpendicular to the wavefront plane. But in fact, you can look into the phase velocity along any directions. And if we pick up the direction to be x direction, then you're going to come up with a phase velocity omega over kx along x direction. And this value is going to be equal to the phase velocity along this the an direction divided by cosine alpha. And it's interesting for you to see that the phase velocity along x direction is larger than the phase velocity along the surface normal direction of the wavefront, because there's a factor here 1 over cosine alpha, and cosine alpha is a value less than 1. And same thing, you can look into the phase velocity along y direction if you project this k along this y direction, and then there's a phase velocity going this direction because there's a wavelength along this pattern. The wavelength basically is the periodicity of this pattern along this direction. So with this ky equal to k multiplied with cosine beta, you can also deduce a phase velocity along y, and is equal to Vp. Vp is the phase velocity along this wavefront normal direction. And you divide this value with cosine beta, which is the angle. This beta is the angle between k and y. Then you end up having a phase velocity along y direction. And if this gamma is not 90 degree, it can be some arbitrary value. Then you can also calculate the phase velocity along z direction. And the phase velocity along z direction can also be larger than the value of Vp. So a short conclusion is that in fact, you can calculate the phase velocities along any direction of the wave. And in general, the shortest wavelength is going to be along the wavefront normal direction, and therefore the smallest phase velocity is along the k direction or an direction. And if you try to calculate the phase velocity along other directions, their value will be always larger than the phase velocity along the an direction. And so there's a phase velocity along some arbitrary direction. We can also calculate the wavelengths along different directions. And again, let's assume gamma equal to 90 degree, so I can plot this two-dimensional diagram. And so given the k on this xy plane, then I can define kx and ky, and the wavelength along this k direction is equal to lambda. But if you want to figure out the wavelength, say along x direction, and so you try to figure out the periodicity of the pattern along this x direction. So you can construct this triangle to deduce that the wavelength along x direction is equal to lambda divided by cosine alpha. And in fact, this value can also be deduced from 2 pi over kx. And this value turned out that to be larger than the wavelength lambda here, because you can see clearly that the length of this blue dashed line is longer than this red line. And mathematically, you can also tell from this cosine alpha in the denominator, because cosine alpha is the value less than 1. And so if you can want to deduce the wavelength along y direction, then just look at this triangle. Then you immediately have this wavelength along y direction equal to lambda divided by cosine beta. And again, this value is larger than the wavelength along the wavefront direction. And finally, if the gamma is not 90 degree, is some arbitrary value, then along z direction, there will be a wavelength as well. And this wavelength is going to be equal to lambda divided by cosine gamma. And its value is also larger than lambda. So in this session, I try to give you some geometric construction for a plane wave. And so we'll look into the k vector along different directions. Therefore, you have a different phase velocity along different directions. And also, we look into the wavelength along different directions. And turn out that the conclusion is that the smallest phase velocity is along the direction of k, along the AN, and also the wavelength calculated along some abstract direction is always larger than the wavelength along the k direction. So this is the a few key points you should remember from this session. Thank you.